In this training video, we're going to study an important feature of data which is found in many loss development arrays, namely heteroscedascity, or equivalently, changes in percentage variability. To illustrate this concept, we will use the triangle group CS5. Now, if you don't have Ecofys Plus open, please open it, and also open the workbook 104A, which you can see here. And I've got the triangle group CS5 already selected, but if you just scroll down or start typing in CS to the panel to find it, double click on it to open it. We'll be looking at the dataset PLI. It is an incremental paid loss triangle. We'll first look at the data itself, so just double click on the dataset to open it, and you'll see something like this. We'll maximize that window. Alright, now you'll see that the triangle itself is not a full triangle, it's actually a trapezoid. We've truncated it to development direction here over here, and we also don't have any data prior to calendar period 1980, so 1981 rather. And the reason for that was that the recording methods were different, and it didn't make sense to combine the two sets of data. Now, the first thing we want to note is that if you look at these numbers here, on a percentage change, there's actually not that much changing percentage-wise. So you've got from, say, 3,000 to 7,000, but most of the time they're sort of around about, only vary by 1,000 too. Whereas if you look out in the tail of the development pattern, just looking at the raw numbers still, so looking at, say, period 10, you've got the smallest value is 20, whereas the highest value is 656. So on a percentage scale, there's an extremely wide variability there, and much more so than looking at the scale down here. Even though you're talking thousands difference here, percentage-wise, there isn't actually that big a difference. So what you see here, and this is common in loss development arrays, is that your volatility or percentage variability is a lot higher out in the tail of the triangle of the loss development array. So by way of example, if you've got numbers with an average of $100 payment that typically have values between $90 and $110, the percentage variability is 10%. If you have an average value of $10,000 with values between $9,000 and $11,000, then the percentage of variability is still 10%, even though you're plus or minus 1,000 now. On the other hand, if the values at $100 vary from $20 to $200, then the percentage variability is a lot higher compared to the values of 10,000 plus or minus 1,000. Heteroscedascity is where we are in the situation where the percentage variability changes, and that is that your residuals or your data are not homogeneous in regard to the distribution. Right, to illustrate this, we're not going to find the best model for this data. Rather, we're just going to illustrate how to model the changes in percentage variation. So the model itself is not bad as such, but it doesn't capture all the salient features of the data, because this is not important for this exercise. So I'm just going to restore that triangle and close that window. Right. And we wanted to have the triangle group window selected. One way of getting this is just to right-click on the triangle group tab and select CS5. And if this window isn't displayed, just click on this triangle group view button here just under the database tab, and it will bring up this window. Alright, so make sure the paid loss incremental is selected, and just click on the triangle group tab, the PPF tab, which is to the right of the triangle group tab. Okay, we've then opened the SGI model. We've opened the weighted residuals plot model displays. We'll just minimize regression tables, so click on the downward arrow, minimize regression tables. Okay. For illustrative purposes, we're just going to do this fairly quickly, so just click on the maximize residual display, and we're just going to add model parameters at 1 and 2 on the development direction, that is, 2 and 3, 4 and 5, 7 and 8, 8 and 9. Okay. We're not necessarily adding the best parameters here, but rather removing enough of the structure to examine the heteroscedascity. So once you've added those parameters by left-clicking in the development display, just click E to estimate. Alright, now if we're just looking at the residuals, I'll just maximize the development display by clicking on the title. We can see just by looking at this that there is very definite change in spread here, so that the volatility is a lot higher out in the tail, and this is exactly what we'd seen when we looked at the actual data just by eye. Okay, so you can also see this just by the change in the shading as well of where those contours are lying. Similarly, if you look at the weighted residuals versus fitted, just maximize that title, you can see that the higher values tend to be close to the line, so that's the higher values on the right here, whereas the smaller values are on the left hand side, and then can be much further away from the 0 line. And both of these indicate heteroscedascity in the data. Now, the other thing is, if you look at the model display for a moment, so click on this model display button. It's the icon at the top here, just under yellow F on my display with the blue squiggly line. Okay. If you look at the shape of the development pattern, where you're getting the high volatility, which is down at this portion here, if you remember the residuals, is where you're paying the least amount. So it's similar to the example that we had earlier. If you're paying really small values, but on a percentage scale, they're a lot more volatile. Now we can examine normality as well, so click on the hourglass with the green diamonds. It's just under here, diagnostic tools. Okay, and you can see from the normality display that we don't have normality. If we're looking at that p-value, we would reject the assumption of normality at the 1% level. If we examine the outliers tab, so just the tab here, outliers, if you look at where those outliers are actually located, they're all in development periods 9 onwards. So exactly the same things that we've seen before. If you're looking at the residual displays for a minute, to come back to the weighted residuals plot, the green diamonds, all the outliers are in this part here. Okay, which is another indication that you've got heteroscedascity when all your outliers are occurring in one area of the triangle. Alright, so what do we do to resolve this? Well, we need to measure those variances, so in other words, to measure the spread, and then use weighted least-squares to adjust for that. So if I just switch to the PowerPoint slide for the moment, what we're looking at doing, okay, is what we've got is a situation where we've got these points that are high vet, we're paying a lot of money out, and we've actually got lowest percentage of variability, so we're in this case down here, and when we're forecasting down the triangle, and we've got smaller values, we've actually got higher percentage variability. Now what we want to do with fitting this regression line is to give the higher values, which have lower percentage variability, a lot more weight than the observations which we expect to vary a lot more. That is, we don't want to try and bias our line to fit these observations if we know that they're going to vary a lot more. So what we need to do is to apply weights to our observations to ensure that these observations get more weight on the regression line than these ones. And the way to do that is to use the inverse of the variance. So that is, the smaller the variance is, the more weight the observation gets. And the higher the variance, the less weight we give it. Okay. And as I said, to do this, we set the weight to be 1 over the variance. Okay, so let's look at how we do this in Equivis Plus. We'll just switch back to Equivis Plus, and we'll look at doing it via manual hetero. So that hetero analysis is this H button here. Don't actually click on it. And you can see the blue H with the distribution there. Click on the downward arrow and open up manual hetero. Click there. And we see a display like this, and we'll just click on the residuals versus development here for the moment. Okay. And again, as we saw before by eye, it looks like we're going to get 3 pieces. If we just look at the shape of these contours, between 3 and 4, and I'll just click on them to put the grey bars in, and 8 and 9. So where I'm putting the parameters is the same idea as accident, that you're having level changes. So we're saying this is one piece of hetero, this is one piece, and this is another one. We could fit these, or we could just say fit all variances. We just click on this button here. That will fit all the variances, and if we look at if I just click on the title bar again, we can see we get a set of box plots, and this confirms what we said earlier, that we're getting one set here, another set, and then another one. So if we click optimize, the double O down the bottom, the blue double O, all we're talking about optimizing is these variances. It's gone and put in those parameters where we suggested initially, that is the 3 to 4 and 8 to 9. If you wanted to remove these parameters, you didn't like what the optimization was setting, you want to put them in yourself, just click on this lower left button here, and it will remove them. Note, until you click apply down the bottom, you haven't actually changed anything in the model. But I actually do want to add those parameters between 3 and 4 and 8 and 9, so put them back in again, and click on this downward arrow, fit current variance parameters. Okay. Now we're going to add them into the model. So click apply. Go back to the model display. And now you can see that we've got the development pattern still the same, but we've also got this variance structure here is different. We're no longer seeing just a constant variance. We're seeing low variance, middle variance, and then upper variance. That is, the changes in variance that we saw originally are now part of the model structure. And if we save that model now, I'll just call it with hetero. Save. If we look at the residuals, we can see that the residuals are a lot more evenly scattered. We're not observing, particularly versus fitted, we're not observing the same volatility being low at this end of the triangle and higher at the smaller end. If we believe there's more volatility there, we can go and check it in manual hetero. So let's do that now. Go to the drop down arrow, manual hetero, fit all variances, optimize, and we see that it actually hasn't added any new parameters. So based on the test that we're doing, we're not seeing any need to add more parameters. Let's close that now. Alright. Now, if we examine normality, click on the hourglass with the green diamonds, go back to diagnostic plots, we can now see that the assumption of normality can't be rejected. We've got greater than 50% for our p-value. Now, if we clear the hetero, okay, to clear the hetero, you can do it two ways. I just clicked on the model display there. But if you go to the drop-down arrow, you've got the option clear hetero. You can do it that way. Or we can go to the residuals display and just click on the top button here. And then estimate. Right, now if you look at the model display, you can see it's now constant variance in our model. And if we look at the residuals, we're back to the stage that we don't have hetero. Now, what we can do is, rather than going manual hetero, fit all variances, optimize, we can just do the step 1, step hetero on this drop down. If we do that, it'll do one iteration. So it'll do, as I said, fit variances, optimize, and apply. And what we can see there is that it's added the same parameters that we did initially. What we can then do is say, well, is there another iteration? Well, we know there isn't, because we did it manually, but we could do one further step. And it comes up with a message that no further changes are required to the hetero. Now, if we come back to that previous model, to do that, go to the logbook and just double click on that run for, because it's before we apply the hetero again. Minimize that. If we wanted to do all those steps in one step, so doing one step optimize, checking for changes, doing it again, we can do the automatic hetero, which is just equivalent to clicking on this H button here. And what it will do is just do all those iterations. It will come up with a message saying that it's applied the hetero, and then you see that changed now. Alright. In this case, we actually know there was only one iteration performed because we did that test ourselves. Very often, what we find is that the hetero structure is a reciprocal of the development pattern. So here it's not quite, but if we're looking at a development pattern, and I'll just come to PowerPoint to draw it. Just find a flag with some space on it. Just bear with me a second here. Yeah. Where's this one? Here we go, this one will do. Sorry about that. Come up to here. Okay. If we're looking at a development pattern that looks like this, so if it just decays down, then more often than not, so this is our development gamma, then our hetero generally looks something like this, with the increasing volatility out in the tail as we go down. Alternatively, if we have a development pattern that looks like this, we're paying out money a lot later in the period, your hetero structure might look like this. Down, and then increasing again out in the tail. So generally we don't observe hetero greater than, say, 2, but occasionally with very volatile data, for example medical data, you can observe it a lot higher than that. Alright, as we'll see in a subsequent video, the modeling wizard also includes hetero analysis as part of the script that it runs. That concludes our section on CS5 and hetero. Thank you.